Okay, then yeah, we just start now with the second lecture of Christian's mini-course on diffeological groupoids. And yeah, let's just go.
Okay. Good morning. Let's oh, I'm doing it already, but then I have to put my notes somewhere else. Yes. Oh, that's a good idea. It's not really my iPad stuff. Okay, so let's get right to it. So as I said, the notion of diffeological spaces, formalizes the sheaf properties of families, smooth families, parameterized by real parameters. So here's the definition. Diffeology on a set X is assignment of du of a set, so it's a subset of P of set maps to X for all open subsets are n's, arbitrary n, such that the following three properties hold. So one constant map is, oh, I have to add something. So these maps in here are called plots. So constant maps are plots. So this, and X is a plot with our restrictions are plots for a cover open cover, just the usual concept. And F, another open subset, could also be of different dimension. This is smooth. Then P. Okay, you clearly recognize this as sheaf properties. I'm going to say in I don't know, 15 minutes, I'm going to say this exactly. So a set. So the pair, let's write in this X XD is called logical space. For the structures like logical space, you usually just denote it by X and the D is implicit. And so a map the sets of two logical spaces is called, well, it's morphism of the logical space, but people also just say smooth. If it maps plots to plots. This forms a category Diffeology. That's diffeological spaces. I give you a tour of examples before that I sort of give a less explicit, give you an interpretive definition that uses the word sheaf. Okay. So the first class of examples numbers. Sort of the baseline examples that just state that known stuff can be viewed. Okay, that known stuff can be viewed as diffeology, as special cases of diffeology. So to sort of see what generalizes. So A sort of is a manifold of usual smooth maps is a diffeology, a natural diffeology, a manifold diffeology. It's not entirely canonical topology. So, and then if you have a manifold and you have some subset, then you have a subspace diffeology. So S has a subspace diffeology. To find totally analogous to topological spaces. So, so P is a plot position with embeddings. So P sorry. That's not so let's see. So that might now be a surjective map. So the quotient diffeology is the smallest diffeology such that pi is smooth. And practically it means that every plot in the quotient topology mapped to S has a local lift around every point. Local lift to plot on that. Okay, good. It's really nice if I can use some lectures. Okay, so that's not so spectacular. So here's what's more to the interesting of this workshop. So the space of smooth functions between two manifolds. That's a functional diffeology. By two homotopes. So D is smooth, so it's infinity maps of U and a subset of the set maps. Way using this exponential object property of this of the set of maps. Okay, so very good. So the very least this does to you is gives you some nice terminology, and here's a nice appreciation for this. If you know the nonlinear Petrus theorem, the Petrus-Slovak theorem, the way it's stated, there preserving the diffeology of being smooth in this definition is called regular. So here's a short version of the theorem. Can be stated as if you're talking about sheaves of sections between smooth fiber bundles, and the statement is every morphism of diffeological sheaves is locally a differential operator. So that's a super nice, I think, super nice way of formulating this if you like diffeologies. Okay, very good. But it's all things you know. So then the first examples we've seen that have motivated on this. They inherit their diffeological structure as a sub-diffeology from these functional diffeologies, right? So a bisection is a section, so it's some map between smooth manifolds. And then in the way we've defined subspace diffeologies, they inherit a subspace diffeology, and then you check that it's a diffeological groups. So group objects in the category of diffeological spaces, and so yeah, but of course very special ones that still have access to an underlying finite dimensional manifold structure by coming from the groupoids. And then you can build new stuff out of that, of course. So you can, for example, consider actions. Action. So of the bisection group, a space of smooth sections. As a group, field theory would call it a field, a space of fields. And for example, if that action is local, as many in physics, this is certainly also diffeological. And the inverse is almost true. I've just mentioned Petrus' theorem, the nonlinear Petrus theorem. This covers much ground in classical field theory, is that action groupoids of bisection groups acting on spaces of fields are diffeological spaces, and they're groupoids. And the question will be, okay, so what are the properties, what are the good properties I need for them to have a, for example, infinitesimal object for them? Okay, but these surely fall into this diffeological world. Okay, so that all looks very nice, but of course it's all stuff we can describe otherwise, and now we come to the examples that tell you a bit that you shouldn't be too happy about this category. There is, so on set X, the local constant maps to X from open subsets of Rns by a diffeology. Or other words for this fine, sometimes you do quite fine diffeology, but we call the smallest diffeology, because since constant maps are always plots, and then this is supposed to be sheaf, so constant maps is not a sheaf, but the smallest sheaf containing constant maps, the locally constant maps. That's that. So the other extreme is, so again in a set, so D all maps from U to X is course largest, since every diffeology is contained, every DU is contained in that set by definition. So that's the biggest one you can choose. Okay, and what else do we have? Somehow, I think I got my labeling wrong somewhere. I already have an F. Why do I have an F? F, G, H. So H comes after G. Okay, good. So what else do we have? So if X is topological space, then DU maps the diffeology. So the continuous diffeology, And perhaps his last remark is that the construction of the subspace and Poisson topology that I've given to you is works for any diffeological space. I didn't really need that. I'm doing this for manifolds. So subspace she works. Say well, let's not find it. Let's say for diffeological spaces, it's not just manifold. And you see that means you can do pretty crazy stuff. Okay, so you take a function space, smooth functions, you take an arbitrary subset, it will inherit some diffeology, because it will be arbitrarily bad. Okay. So I haven't even, in the interest of time, not giving you the crazy stuff. You can define really weird diffeologies. The classic thing is, the classic counterexample is the so-called spaghetti diffeology. So where you require on a smooth manifold, you build a manifold with a different diffeology, and the condition for your plots is that they are of rank at most 1. So meaning the images are all ions, and you can generalize this. You can define rank restricted diffeologies. So if you require this to be of rank at most 2, I don't think this is a known term, but I would call this the fettuccine diffeology, and of the 3-dimensional pasta, like K rank diffeologies that I use as counterexamples that you always need in this business. Why? Well, this tells you, the last batch of examples tells you that this category is way too general and large to allow for good geometric results. Since everything you prove must be true for all that stuff, it must be thinking you're doing some differential geometry and then you're proving something that also needs to hold for topological spaces or just sets or crazy stuff. So what you need, for example, is a good set of counterexamples of examples that do not come from generally geometric, let's say familiar geometric situations, to keep you from trying to prove stuff that simply is not true and you think is true because it's informed by a geometric division. So at any rate, so the task, whenever you then want to do actual geometry in these settings, is to find good addition conditions that give you what you need to make your theorems true, to have the tools you need, because a priori you've given up everything, every bona fide analytic or differential geometric tools. There's no inverse function theorem or Hadamard's lemma, where if you need this, very basic stuff, and you have to, if you give up everything and then you try to add conditions to have it just enough for you to prove your stuff. And then, of course, the difficult part is to find conditions that you can check, and conditions that have a, let's say, added value to just being the conditions of your theorem. Okay, so you want to have some nice general, relatively general class of things that you can prove many theorems from. So, okay, but this is just sort of a sort of philosophical remark. If you venture into these categories, pre-sheaves and something, and everything exists, and then so you have to work hard to find the geometry again. Okay. So what I want to do, what motivated me, I wanted to have something like a differential calculus on these diffeological spaces and find the conditions that you need to impose them for this to exist. And other people may want to do other things. That's what I wanted. I wanted to have something like, be able to have a Lie theory for diffeological groupoids, for example. Now you go back to the original constructions and try to find what you need and then formalize it in these categories. Okay. So the first thing think we might need for a differential calculus in diffeological spaces is a tangent function. So, what you do, you go to your favorite book on diffeology and just look it up. I mean, this shouldn't be the first thing people came up with. Okay. Well, not so fast. That's what I try to do when I taught the lecture on Nico's classical field theory and realized this doesn't exist. There is a whole zoo of tangent functors defined in diffeological spaces. And the first paper I looked up started with a sentence. The definitions for tangent functors of diffeological spaces broadly fall into two different classes. Okay, but I'm in trouble. Okay, so so let me explain why. Okay. So here are the reasons. I see it. Okay. So the first reason is that on smooth manifolds you have several definitions that you may prefer, but they are equivalent, that become inequivalent on diffeological spaces. That's a very legitimate reason, and you might want to do different things with this, so you might need different definitions. So definitions spaces. So the classic ones, definition on charts, transformation property, the physics definition, so find physics book. So B by equivalence classes of smooth paths. So that's what people call the kinematic definition, typically. And then C by derivations. So derivations of the ring of smooth functions from vector fields, so derivations at the point of tangent vectors. And they all become inequivalent. And the second reason, I think, is a less justified one. So the second reason is that some authors they force the tangent fibers vector spaces. So that, for example, why don't I like this? Well, the space in diffeological spaces you should think of as space as in topological spaces. There's no manifold structure whatsoever. Nothing's modeled on a vector space a priori. Of course, there is a notion of topological manifolds, but for topological space, that's not the case. So I don't know if you see it, but in my geometric notation, for me, the tangent fiber at a point should be something like an infinitesimal model of the space at that point. So it should look like the space. So if I take the subspaces of Rn, well, I could take an open subspace. Okay, so it's all there. There clearly I have the usual notion of tangent fibers, tangent space. That should be vector space. That looks like a vector space. But all the constructions, since the information, the vector space information is naturally there in the Diffeological space, sorry, it has to be forced to the vector space by universal construction. So it's typically a free vector space in some appropriate category. So the categories mostly cones, are cones, because we always have the arm multiplication scaling of tangent vectors in all definitions. So if you take this as your subspace of Rn with the subspace diffeology, and you apply these constructions, the tangent space at the origin here will be also R2. So it's not just that, for me, this is not a good idea to have the tangent fiber of this at that point PR2, at least not for the primary definition, but you also lose information. And then if you have something like this, subspace that looks like this, how many lines do we have? 1, 2, 3, 4. So just these lines with subspace topology, you construct the tangent fiber, this linear construction, this would be R4 at the point. So it looks like something higher dimensional that it's not. So, okay, that's my motivation, by the way. I don't want to do this. Some of us do, and that's one reason for integrating different definitions. I mean, if you want to do absolutely insist on doing homologic algebra on these spaces, then you might want to force it to be vector space at some point, but it's really just a matter of convenience and a universal construction that then may break other things. So the third reason, I think, is the poorest reason why things are different. Some authors and some in the classic definitions, they first define the tangent fibers, the tangent spaces at points, and then, as a second thought, think about how the whole set of tangent fibers or tangent vectors on the entire diffeological space has to be diffeologized, so put with smooth families. And this you can do it several ways, unless you have a good principle like universal property or something got to do with it. This may lead to equivalent definitions and outright errors. The things in the literature where people just get it wrong. So, well, I think I've said it. I don't need to write it. Okay, anyway, you can look it up in the notes. Okay, so since I want a lot of structure for the calculus, as I realized, going in these ad hoc ways didn't work. So I'm going to take now, at least for the purpose of explaining in this talk, from the kind of total perspective of having set maps with properties to a more equal perspective of category theory. So here's now the sheaf definition of a diffeological space. So this is proposition 6. Space. Is a sheaf say called Euclidean space, but I call Euclidean spaces of open subsets. So the usual site, our most cherished large site in different geometry of subsets. Well, that's a nice and concise definition. And the only word that I think needs to have some explaining is concrete. So category is complete because there's a forgetful functor to sets. So every object then can be viewed as set with structure and every map as a map of sets with properties. Okay, so for a concrete sheaf, we first need a concrete site. There's a bit more specific. So a concrete site has that the functor points as the terminal object usually considered to be the forgetful functor. The factor of points is faithful. And Max covers functor, so that covers, I mean, like the union of our open subsets that map to what is being covered, they map that to a surjective map. And a complete sheaf, means that it's a sheaf with concrete site with the addition property that it's a subset of the set maps. So it's a subsheaf. So the P of U is a subsheaf. So if I write it correctly, of the horns from the underlying set of the U. What is this? This is the function of points. That's going to be the X, and that's something we have just, as it's customary in topology and geometry, we haven't spelled it out. So if you talk about the definition of plots, the plot is a map from U to X such that then I view U in that part of the sentence as a set. So I'm implicitly talking about set maps of the underlying sets, not of the objects that I'm actually writing down. They're not even the same category. So here I'm just spelling it out, but we usually would just call U. Okay, that's our X in the definition. Okay, anyway, so now you see this is just a fancy terminological translation of what I've written down explicitly in the first definition. And this was, I don't know, it's because it's kind of obvious, this, people attribute this to bias Hoffnung, but this is the fact that it's a concrete sheaf on the side of Euclidean spaces, diffeological space, that's one observation. And then they spell out in large detail all the categorical constructions you have on this category explicitly in terms of plots. And that's at least one of the things they do. So now that you have it, so why is this good? Okay. Now you can go to your favorite handbook of category theory, things that are a bit scary normally, like Topos theory, sketches of an elephant, part 1, and look it up. What kind of category this is, and then you can, they figure this out on general grounds, and something that would be, I think, really hard to do it for plots. It would be very lengthy, but anyway, something known we can take from the literature. And yes.
Does the proposition given equivalence in the diffeological space is the same thing as the complete?
Yes.
Example.
Yes, it's the same thing. There's a slight difference, a small difference. Okay, what do you mean by subsheaf? Of course, you have to say. So here we really identify a sub-object in sheaves could be given by an injective map with its image, which is an actual subset.
My question was the Poisson is the same thing as the
yes. Yeah, it's really the same thing. If you write it down, it's kind of just a translation of terminology almost. But the only thing that perhaps needs a bit thinking is that every morphism of sheaves is given by a map of the underlying sets. That's the only thing I need to check for myself to be sure.
Maybe another question. Could you replace here open sets in Rn and smooth maps by all manifolds by manifolds and smooth maps even in the first definition? An equivalent notion of diffeology?
Yes. Yes. But it's more convenient for technical reasons here. So the Euclidean spaces sits inside manifolds, and this sits inside diffeological spaces, and the functor is the first functor of then is faithful. And now if you do things like gluing, like Kahn extensions, that's categorically speaking, that's Kahn extensions, so the Kahn extension along the whole embedding from Euclidean spaces to diffeological spaces is the Kahn extension of the first and then the Kahn extension of the second. The first one is just gluing of an atlas. The second one is then gluing sheaves and manifolds to diffeological space. And this is, so in that case, this is the same operations. I mean, this is the technical answer of why I say yes at this point. I Okay.
Can I ask you to be a tiny bit more explicit? Not explicit about this. So I forgot what the site is. So is that a category with more data? So can you say one line definition of the site?
Yes, just we don't have to. This is too general for the talk. Just think of the open subsets of Rn's and the covers as distinguished maps. And then they satisfy properties like covers of covers are covers. Okay, things like this. So if you have a cover and then you cover every UI of the cover again and you put everything together, that's again a cover, but it's all you know from like if I wake you up at night, how to deal with these. And site is just an abstract version of this. But I think you can safely forget about that you can do this for all sites. Just think about the usual sheaves, as you know.
So in the word sheaf there means functor from functor to sets. Right?
Yes. Right. Sheaves and sets, or sheaves and sets. But if you say, what is this concretely? I've spelled it out. That's the first definition of diffeological spaces. So the DU is the sheaf. That's the assignment to you of a set. And now, since it's concrete, it tells you it's a subset of all maps from U to this X. And then it has sheaf properties. I've spelled them out. And so you can take, if you don't like the abstract version, take the plot one. Okay. So it's perhaps a matter of taste. I think in bench is that you can now connect to a whole and sometimes somewhat disjoint body of knowledge from category theory and like take the good properties just from the handbooks. That's the very least you can do. And then you can retranslate them, of course, into statements about plots. And this you can look up in this paper by Bayes and Hoffman, for example. So here's the proposition. Are there more questions? This was too fine, sorry. How good this can be. I'm just throwing some category theory adjectives at you now, and if you don't know them, don't worry. If you know them, you may appreciate them. And the message is that for the theorems that I need for this to work, I need all of them. It's not just fancy stuff I want to brag about. I really need all the properties, also adjectives I didn't know before. Okay, so the category of concrete sheaves also for e.g. logical spaces is focus with strict, what is it called? Strict initial action. And instead of explaining to you what this is, and then you're still not wiser, I'm going to spell out a few properties that you may appreciate. I do. So it immediately follows that the category of diffeological spaces, well, let me phrase for diffeological space. I don't need to for its generality has all small elements. Units, exponential objects, memory spaces. So this is, I mean, I don't know if this, Peter, you can correct me, it's what I would call it like a convenient setting for differential geometry, they say an ambient category for this. It's also is locally Cartesian. This means that you have also right adjoints to not just the product, but the fiber product of a given object. That's very nice and conceptual. Then your monomorphisms and epimorphisms are really nice. So the strong monos and strong epimorphisms. So a strong mono has a right lifting property with the right lifting property with respect to all epimorphisms. And that's nice, but relatively weak condition still. An effective means it's really an equalizer of a specific diagram. Particularly it's regular. So think of it as intersection. Intersection space. And what else do we want? So then strong monos and strong epi's are stable. Complex. Then so this quasi-adhesive out of strong monos complex. This is kind of a stand-in for short exact sequences in this category. Co-products are disjoint. So really behaves like spaces and not like, say, algebras. The co-product unit algebras, they would all contain the unit and to me a disjoint. And finally, then I'm going to be over with this categorical excursion now. Well, not over. This throwing terms at you. Is and that's really nice and has some practical consequences. Good consequences that the number of points factor, which maps from the diffeological space to the underlying sets, has a left and right adjoint. Particularly nice because it tells you how to construct limits and colimits. Since it has a right left adjoint, it preserves colimits and limits. So you just compute them in sets, and then you figure out what the diffeology is, which is also very easy to say. Okay, so it behaves really nicely also for practical purposes. So moreover, we have unit embedding that was units already asked about. So unit small y that places within spaces, or you could take manifolds spaces. That's faithful. So that's really the usual stuff you're doing with working with differential geometry sits inside there. It's also dense, so it's faithful. spelling out a version of the Vienna lemma in a way that you may appreciate as sort of a generalization of the geometric construction. This means that every diffeological space is the co-limit of its plots. So you don't need to wrote the plots just as so. So this was a set. This was a like a smooth thing, and that doesn't match up. And now here I'm trying to be careful and have Vienna embedded. That's what's really meant here. And so this maps to this now as a diffeological space. And again, people often would just drop the y and identify the u with the u sitting inside x, but this is the dangerous here, since we then may forget that, for example, y does not commute with colimits. That's really that doesn't. So every diffeological space is the colimit of its plots, the domains of its plots. So why do I emphasize this? Well, that's the analog as you have for manifolds. So every manifold is the colimit of its charts. So meaning you take the charts, the colimit is the gluing operation, and that gives you the manifold. So here this is the analogy to having something local, the u's, the plots, the names of the plots are now the surrogate for the charts, and still true that if you glue them with the colimit, you get the x. Now, categorically speaking, that's an obvious fact, but I just want to attach some geometric intuition to it. So this tells you that this suggests of how you generalize the local construction of manifolds that you can define on charts and then glue together how you generalize those to diffeological spaces. And I think this is from what I want to do with it. This is the only reasonable way. Okay. So that the member factor of the Euclidean spaces, for example, the tension factor, then left-hand extension of the Bonita F, then it's target Euclidean space, you place a diffeological space for this to exist. So you could write this as the colimit of the extension. What I just said. So you apply F, usual F. First, let's call this F hat. Okay, so the hat is the one that's in the Euclidean spaces, and this is my extended F. So I do this, and I place it in diffeological spaces. Is the only this gluing operation. And so the picture you have is it sits inside the data embedded. Everything works out, and this here is your F. Okay, so this is how this works, the natural extension compared with colimits. And the nice thing is, yes.
Can you say in one sentence the last stuff that you wrote? So are you saying that any functor had from this category of open subsets of Rn itself has a unique extension to logical spaces, something like this?
No, it has a unique extension that is compatible with colimits, that preserves colimits, right? Which means that it's on, like, it also means that if you evaluate it on, or by virtue of y being faithful, if you evaluate it, this is a commutative diagram. So you evaluate it on on an open subset of Rn, you get back the old functor. Okay, condition 1. And condition 2, the functor applied to the co-limit is the co-limit of first applying the functor and then taking the co-limit. That's the condition. And so the nice thing about this is that, that since it's given by universal construction, it has additional nice property. So let me.
I'm sorry, Christian.
Yes.
May I ask something? So do you mean f is the functor, which is the left-hand extension of y f hat via f? But then when you write it as a co-limit, you mean f evaluated at x, right?
So thanks. This is that's confusing. Thanks, Laurie. I said I'm giving you the pointwise. It's a pointwise time. Essentially, sorry, this was confusing. Thanks, Laurie. Okay, good. So, so the statement is I have a functor, the left Carnot extension along y of some functor, the f here, which goes from functors in spaces to functors of logical spaces. So in this first sentence, there's already a very good statement hidden. It's a functor. So what are the categories? So now you have all endofunctors of the same category, and functors are two categories. So you have functors and natural transformations. So in terms of differential coordinate changes on Euclidean spaces. And so the category here has its objects, the endofunctors, and its morphisms, the natural transformations. And having a functor meaning it takes a natural transformation here. So any natural construction you do on Euclidean spaces as the tangent functor, or the, let's say, the bundle projection of the tangent functor, okay, that's a natural transformation. It's not to a natural transformation here. So it's a high level of compatibility. So this is, it has two additional properties, so it's fully faithful. And more importantly, monoidal. So since it's endofunctors, you can compose to endofunctors. That's a monoidal structure on your category of endofunctors. And the Kahn extension also is monoidal, meaning the Kahn extension of the product of two functors is the product of the Kahn extensions. That's the nicest possible construction you can think of, okay, for natural operations on defined Euclidean spaces. Okay, and so let me just of time. I'm going to skip something. Anyway, so the natural, that's why I call these the natural extensions, are really natural also in the sense of natural constructions in geometry or in, you know, Peter Biesch's collaborators have taught us about a great deal. And in a term like natural bundles, right? That's the same natural. We have 5 minutes, so unfortunately. And I've surely wiped the wrong board first. Okay, doesn't matter. So now for the definition won't come as a surprise. To 8. So that just for the sake of having a differential notation, let T be the tangent functor on Euclidean spaces, so it maps open subset of Rn in 2u cos phi. That's right, without x will be called my terminology will be called natural factor of logical spaces. So in the last few minutes, I tried to convince you that it's not so weird and general and strange as you may think. So what we have to compute to figure out what this is more concretely is we have to compute this colimit that defines the pointwise conic extension. You can also look now you're back in I don't know, McLean chapter 4 or something, how you compute limits, colimits. So let me do this for you. So what is the Tx? Let's call these the plots. And so all these plots. And then I take the T in Euclidean spaces and now maybe to alleviate the notation a bit. Let me place the Euclidean spaces identified with the image and the union embedding. So this sounds it looks a bit nicer. And then this is just the TU and the colimit of this. The TU is this very basic stuff. So what is this? So it's a quotient where you take the coproduct over all plots and you take u, mix it by p because the same u may have different p's, and then the colimit, the quotient. And what's the quotient? So first you can do it in sets by this what I mentioned that we have a right adjoint of the functor, and then in the second step I tell you what the diffeology is. Okay, so what is this? So a vector, say eta q in the usual tangent point of view, that's like the Rn, and eta v domain of a plot are called such that there's a smooth map f from u and q plus such that it's a morphism of plots. So u so this is so and map of f takes and e. So this is the case. So meaning you'd have two different plots. They're related by a smooth map, and the tension vector up here is mapped to that here, so that everything commutes. Then eta u, eta e, or let's call it, just for the sake of the definition, T related. And they are related in this equivalence class, but they are T related by zigzag. So triple is the equivalence relation. generated by T relations. And then you can, that's already a pretty explicit handle on things, also you can completely compute stuff. And perhaps the most interesting point is that since, of course, every tangent vector U is represented by path, you can always choose, if you have something in U, and here you have a eta U, and this stems up to X, that's your P, well, you can always compose it with some smooth map, that's some path representing eta U on U. So now the result is every element in this big quotient is represented by a smooth path in X. So I should call this. So this means what you're getting back, sorry, with the universal construction, with this universal construction is the kinematic definition of tangent vectors, albeit without vector space structure on the fibers. Okay? And just by understanding that this is, and I'm sure not the first one, understanding that this is you obtain the kinematic tangent vectors by Left-Kahn extension, by really nice categorical construction. Now there's hope that the other stuff you have, bundle projections, the flip of higher products of tangent functors, the vertical lift, and other stuff that I will mention and quiz you about next time, whether you knew it existed on the tangent functor, like in the model structure or a cosimplicit structure on the powers of the tangent functor. All this will be mapped by this universal machine to something on diffeological spaces. And that's the advantage. That's just one part that's not being preserved, and this is by the fact that this Kahn extension doesn't preserve limits. And so where is the addition of just a small side remark, so where things go wrong, where we have to think more, is so the addition is defined on TU is hybridized addition, and this is not preserved by that construction. Okay, so it gives you another functor than Tx over x to x. It's not the same thing. This is exactly what we have to fix to get at the end of the day, get a nice differential calculus, and that's what we do next. Oh, I'm over it. So, thanks.
Thank you, Christian, for the nice talk. Are there questions in the audience or online? No. Okay. Maybe first questions online. Other questions online? I see two participants raised their hand.
Yes, there are questions online. Yeah, I think they could just unmute themselves and ask them. And like, let's say start with Peter Michael.
Yeah, I just wanted to point out that there is the notion of a Fröhlicher space, where instead of plots you have just smooth curves, and then you have smooth functions which are smooth along the smooth curves, and then you have to enlarge the space of smooth curves so that they determine each other. And this is a reflexive and co-reflexive subcategory of diffeological spaces. And as far as I have followed now, it seems that your description of tangent functor should go over also to these Fröhlicher spaces. I mean, the diffeological spaces give much finer structure and perhaps too fine a structure. And Fröhlicher spaces is something in between, and it makes use of Blohmann's theorem that the function on R2 or on a Fréchet space is smooth if it is smooth along each smooth curve.
Yes, I completely agree that, of course, Fröhlicher spaces are much nicer from the viewpoint of different geometry, and all the examples I gave you are Fröhlicher spaces, and only the spaghetti diffeology would not be a Fröhlicher space, which is not reflexive. But at the end of the day, I'm adding conditions on my diffeological spaces. And I don't know yet whether this perhaps even implies that they are at the end Fröhlicher spaces. This is a difficult question. I thought about this, but I can't answer if, after I'm doing sort of what I'm doing in the next lecture, I end up with additional conditions that even might tell you that at the end of the day, we're dealing with Fröhlicher spaces, but I'm not entirely sure. Maybe if I give some examples for the kind of elastic, what I call elastic diffeological spaces next time, maybe you will say right from the top of your head, oh, this is Fröhlich or not. You see this more quickly. But yes, I agree. This is much nicer. And then the question would be, are the examples I want to cover or want to apply this to, are they Fröhlicher, or do I need perhaps a slightly bigger, but still well-behaved category? Yeah.
Thank you.
So I have a question. So maybe this is kind of a silly question, but why is there a good technical reason for using, say, the Euclidean site rather than the site of manifolds?
Yes, the reason is mostly technical. Is that on Euclidean spaces you can actually very easily compute stuff. And if you think of what a manifold is, and if you actually calculate something, a manifold, but deal on manifolds with local constructions. And that's all I'm doing here. It's by definition something that exists on charts. And this means there's no real advantage because all I'm dealing with lives on charts anyway. Okay? So if I ever go to something that involves the global structure of manifold, then of course that would be very different.
And then I have another question. For these like tangent spaces that you end up getting, what can you say about, or tangent spaces, what can you say about their structure? Like, are they like vector spaces that are glued together at the origin in general or something?
That's right. It doesn't need to be vector space, could also be single rays. So it look like this.
Okay, yeah.
Right. And what they are arcones. So meaning it sets with an R action on it that is free on the units and maps and the multiplication with 0 maps everything to a single point at origin. That's my definition of R cone. It's not a convex cone necessarily. It could also be just 2 lines like this. That's an R cone.
Yeah.
That's the structure of it. So they are glued together, either rays or half rays, glued together at a single point. It's really the wedge product of this. But of course, it can be sort of, you also have the entire plane, and then you have lots of them where you have this, that would have to glue all these rays together in some sense.
I see. Okay.
Okay, maybe now the physical questions. Okay, I see a physical question.
So I think you already partially answered my question. I was just going to ask, what does the tangent functor give for these examples that you're drawing before? But I guess it's just the gluing of these lines.
So in the examples I drew, actually what I drew is already the tangent functor.
Yeah.
Okay, so that is already a fair representation of what the tangent diffeological space, not vector space, tangent diffeological space looks like. It really is the subspace of our end that looks like this. This is the subspace that looks like this. Only if I now, have a sphere and have something like this. Okay, and I look at that here, we'll have that as diffeological tangent fiber at such a point. In that sense, it really is a local, like a infinitesimal local representation of what's going on here.
Do you also know how to compute these tangents for some more complicated examples, like for example, algebraic varieties with cusps? Because sometimes in algebraic geometry they also have different notions of tangent columns, and it's not clear a priori to me which one that might coincide with.
I will have cusps at an explicit example next time. Okay. It doesn't deal well with self-intersections, but cusps are nice. And cusps even have the nice property that if you have manifolds with boundaries, so that you, for example, squeeze one of the corners to be a cusp, like the curve, x squared equals y cubed. This is still nice in the sense that every tangent fiber is a vector space. That's a bit of a surprise. But then, of course, at the tip of the cusp, it's p0. Because however you pass through this with smooth paths, this will be resting point. So every smooth map will have derivative 0 of that. And you can really, at this point, think of this tangent vectors as very analogous to the huge definition of vectors, tangent vectors in terms of smooth paths, and the same velocity at the point. That's certainly true for subspaces of area.
Okay, thank you.
If I may add something, here's an example that's surprisingly hard to show, and this also will be in a loop. In this loop, when I taught, of course, on classical field theory, and that's something every differential geometer would expect. You've seen it being used already. So the tangent thing of this is really what you would like in this geometric shape that you would expect. And the literature, this was only shown for compact. This would be a bit sad for applications in classical field theory, but it's true, and you have to work a bit harder. I would call this a theorem, actually. That's reassuring. Actually, if this hadn't been true, and at some point, like while teaching this course, I thought that this might be true for a week and then not true for another week, and this went on for a few months. If this were true, I probably would have abandoned the whole thing. Because this is something I want to make the statements that you find in physics book about variations and things in the Lagrangian field theory actually be rigorously true if you express it in terms of diffeologies.
That answers my question, which I didn't want to ask because time constraints, but thank you for answering.
I think there are no questions in this room anymore. Are there still questions online? I can't see this. No, there are no questions online anymore. Then thank you for the last question. Let's thank you again.